Hi, this is Maggie from Design Code Debug Repeat. Welcome to the channel. This is the 7th installment in the Adventures with Python series, in which we learn Python by building a text adventure game. No prior programming experience is needed, but you should watch the series videos in order. I'll link the playlist here and in the description. Let's get started. So far, we've built a functionally decomposed game with a data structure representing our dungeon and a game engine composed primarily of a loop, allowing the user to explore the dungeon until they choose to quit. In this video, we're going to learn about a new data structure called a dictionary. We'll incorporate it into our game and expand our game's functionality. I've renamed our game to shabbyabbyv7.py. It's been uploaded to my GitHub repository with the other code from the series. There's a link in the description. A dictionary is a collection of key-value pairs. It's similar to a list in that it stores multiple pieces of data, but instead of accessing values by their index position, which often doesn't relate to the data in any way, you access each value by its key, which is meaningful. If a list is like lining your friends up and addressing them by their number in the line, a dictionary allows your friends to sit anywhere in the room and you address them by their names. A game-related example might be a dictionary of monster stats, where the key is the monster name, a string, and the value is the monster's health points, an integer. Or the key could be the monster's name, a string, and the value could be a list composed of information about the monster, like description, health points, attack points, walking speed, etc. Another example is a dictionary of healing items, where the key is again the name, a string, and the value is the number of health points restored by the item, an integer. Keys must be immutable data types. Remember, immutable means cannot be changed. Keys can't change. Strings, ints, floats, and tuples are all examples of immutable data types that you can use as keys in a dictionary. Each key in a dictionary must be unique. Values can be of any data type and can be duplicated. The exits component of a location in our Abby data structure is a good candidate for a dictionary. The exits for the cloister is the list 1, 2, 3, 4. Recall that those are the indices in our Abby list of the locations the player will move to if they exit the cloister to the north, south, east, and west, respectively. So, exit north from the cloister and you're at the location at index 1 in the list, the church. We store the information that the element at index 0 is related to the player moving north, the element at index 1 is related to the player moving south, etc., separately from the list. In fact, it's in another list, or tuple, now the directions tuple. For some reason, I have constants for north, south, east, and west that aren't used in the program. I can't remember if I ever used them. They're like comfort constants. Let's delete those. But in the directions tuple, I have directions strings that are parallel to the exits list. So I index into this tuple, get the index of n, and use that index to get the index of the next location. And that's just fine, but if we use a dictionary, we can cut out the middleman and simplify the code that uses this data structure. I'll define exits equals N1, S2, E3, W4. You can see a dictionary is enclosed in curly braces and is a comma-delimited list of key-value pairs. The keys and values are separated by a colon. So N is a key and 1 is its value. S is a key and 2 is its value, etc. To use this dictionary, I can write exits sub n, just as if I were indexing into a list, except I put the key in the square brackets instead of an index, and that expression evaluates to the value that matches the key. You can see why keys must be unique. If we were allowed to have more than one key-value pair with a key of n, Python wouldn't know which value to retrieve when we used the key. Hopefully, you can see how this cuts out the middleman. If the player types n, I can use that to index directly into the current location's exits dictionary to get the new location. So I could simply substitute a dictionary for each exits list. But I don't have to store key-value pairs for exits that don't exist. North from the church, for example, there's no exit in that direction, at least right now, so it's a -1. So for the church, my exits dictionary would be simply S:0, just the one exit. And if needed, we can define an empty dictionary, which is just open close curly brace. I can pass a dictionary to the len function, so I can check if there are any exits, and I can find out how many key-value pairs there are in a dictionary. A key-value pair counts as one element. So if I type len exits, idle responds with 4, not 8. There are 4 key value pairs. And now the cool thing is I can also add an exit to a dictionary, and I can remove an exit from a dictionary. So what if a wall gets knocked down and an exit opens up, or a cave-in happens and an exit gets removed? Let's add an up exit to exits. I write exits sub u equals 5, for example. There isn't really an up exit from the cloister. And if I type exits now, you can see there's a key value pair for u and 5. So to add an element to the dictionary, you just subscript with the key and assign the value. You can also change the value for a key in the same way. If I write exits sub u equals 0, I've now changed the value associated with the key u. To get just the keys from a dictionary, you can type the dictionary name .keys, open close parentheses. So exits.keys yields NSEWU. And this is an iterable. So I can write for key in exits.keys, print exits.key. And you can see this prints each value because I used the key to index into exits. The dictionary is itself an iterable, and its iterator also iterates over the keys. So you can also simply write for key in exits, print exits sub key, and that will give you the same result. I can also get the values from a dictionary by using dictionary name.values, open close parentheses. Let's try exits.values. And this is also an iterable, so we can write for value in exits.values, print value. And finally, we can use items to get key value pairs. Now, if we're going to iterate over items, we need to provide loop control variables for both the keys and values. So for key comma value in exits.items, print key value. To remove a key value pair from a dictionary, we can use del for delete, or we can use pop. They work 2 different ways, and both will throw an exception, crash the program, if the key isn't in the dictionary. To use del, write del and then the dictionary name sub-key of the key value pair you want to delete. For example, del exits sub u. Now if I look at exits, the up 0 key value pair is gone. If I try to delete it again, though, I get a red error message. So if we're going to use del, we should first check if u in exits, del exits sub u, and that will only try to delete the u key value pair if it's in the dictionary, and avoid a crash if it isn't. The pop method returns the value for the key we pop, and we use dot notation with pop. Exits.pop n evaluates to 1, and if we check exits, the n1 key value pair is no longer there. If I try to pop a key that isn't there, I get a crash. However, I can pass a second parameter to pop that it will return if there was no key with the past value. So for example, exits.pop n -1 will evaluate to -1, and it won't crash even though n is no longer in the dictionary. You can also check first with in before sending the pop message, as we did with del. So, with all of that knowledge, let's modify our data structure so we have dictionaries for the exits. I'll include only directions for which there are exits. So, for example, the cloister exits dictionary is N1, S2, E3, W4, and the church exits dictionary is S0. This dictionary is replacing the original list and is still at index 2 in the list for each location, so the exits constant is still correct. I'm going to comment out the call to get exit string. We'll see how to modify that next. For now, let's modify the code that moves the player in the direction they've chosen if there is an exit in that direction. We won't need that middleman of the directions tuple any longer to find the index of our direction in the exit sublist, so we'll remove the line of code that sets the location index. We no longer need that variable, so I'll also remove the annotation. Command, remember, holds the first letter of the direction the player wants to move in, and we've already confirmed that it's a proper direction. Now we want to check if it's a key in the exits dictionary of the current location. We can do that with if command in Abby sub current location sub exits. And if it is, we will set current location to Abby sub current location sub exits sub command. The command string will be the key for a key value pair, So Abby sub current location sub exit sub command will evaluate to the value, which is the index of the location the player has now moved to. And if I run it, it doesn't tell me my exits, but I can successfully move in directions for which there is an exit. And I just stay where I am when there isn't an exit. And bad commands are processed as before with an error message. And I can quit. Now, getExitString is the method that previously took the list of exits and turned it into a string describing the exits. Let's change the name and annotation for the parameter. It's no longer a list of int, so I'll call it exitsDict and annotate it as a dict of string, int. The function starts with a list comprehension that turns the old list into a new list of only the available exits. We need to change that now to turn the dictionary into a list of the word versions of the keys. In fact, I could comment out that list comprehension and replace it with exits equals list, open parentheses, exitsdict.keys, open close parentheses, close parentheses. That will take the keys and cast them to a list. Cast means change the data type of. You can change some values in some data types into other data types. We can change the type dict.keys, which is what the keys method returns, into a list. So if I do that and uncomment the line down in main that invokes getExitString, I get, you are in a courtyard. There are exits to the N, S, E, and W. Well, that's pretty close to what we want. It's just that it's the letters and not the words. How can we turn those into words? Take a look at our directions and direction string tuples and see if you have an idea. Here's my idea. I'll resurrect the list comprehension, iterating over our keys and using them to index into this tuple. So for example, if I have the key N, that's at index 0 in directions, and I want to use that index to grab the string at index 0 in direction string. So I'm going to write exits, which is still a list of strings, equals open square brackets. I'm going to skip the expression and get to the loop part, for key in exitsDict. I'm writing it that way because it gives me the variable name that's going to be in my expression. Key will be a key in the exitsDict, so the letter N, S, E, or W right now. Now I'll write the expression. I'm going to use the key to get at the string I want, and for each key in exitsDict, that string, if I write the expression correctly, will be added to the exits list. So I want to index into directions string, so directions string, open square bracket, and I want to use the index I get from directions, so directions.index, open parentheses, key, close parentheses, close square bracket. Something like this is easiest to read inside out, in my opinion. We're getting the index of key in directions. Remember, key is a direction letter. If it's N, for example, this expression will return 0, the index of N in directions. S is 1, E is 2, and W is 3. We're then using that index to index into directions string, where 0 is the index of the string north, 1 is the index of the string south, etc. And when I run it, this works as it did before we changed our data structure to a dictionary. Now you could change an entire location into a dictionary. You might have name, description, exits, and visits as keys, and the values would be the values we have in the list right now. I'll leave it as an exercise to you to change the locations to dictionaries and rewrite the game engine code to work with that new structure. I thought it would be more fun to add some new functionality, inventory functionality. I'm going to add an inventory dictionary to each room, and I'm just going to make a dictionary of name-description pairs. The key is the name, and the value is description. And for some locations, we'll have an empty dictionary, meaning there's nothing there. Let's add an inventory to the end of each location's list. For the cloister, I'll put an empty dictionary, 2 curly braces. I'll put the book in the church. So, open curly brace book, an ancient book with a decorative leather cover. And I'll give the kitchen 2 things, a knife and a skull, so we have a few things we can take and drop. I'm going to put an empty inventory in all the other locations. Now, if you've already converted each location to a dictionary, you can have the key for this be inventory. My locations are still lists, so I'm going to define a constant inventory and give it a value of 4, the index of this inventory dictionary. And let's add some more constants. Take commands, a tuple of t and take. Drop commands, a tuple of d and drop. inventory commands, a tuple of I and inventory, and examine commands, a tuple of X and examine. We can't use E because we're already using that for east. And down in the game loop, we'll add some more elifs. Elif command in take commands, elif command in drop commands, elif command in inventory commands, elif command in examine commands, and I'll put pass after each one to start, just as a placeholder. Now, if you took my practice advice at the end of the functions video, you already wrote a function that will handle exchanging items between inventories. Yours implemented the inventories as lists, but this will be similar. We'll call that function if the player chose to take or drop. This means we'll need a player inventory. I'll define that in main. Player inventory of type dict string string equals the empty dictionary. That's the same type as the room inventories, and it will start out empty. Now, we have a slight problem here. What is the player trying to take or drop? This will be a two-word command, like take book or drop skull. We'll need to do a little command processing to separate the words the player may have typed. We can use the split method to split a string into a list of the text components that are between whitespace. We call these text components tokens. If the player typed take book, split will separate that into a list composed of take and book, the two tokens separated by a space in the original string. But if they typed just take, split will give us a list composed of just one element, take. I'm going to annotate a list of strings called command parts, and after we obtain the command from the user, I'm going to split it and store it in this list. I'll then convert command parts sub 0 to upper. That will be the first word the player typed, which might be look or quit or something unexpected, but it will be the same as before. Right before that, I'll make sure there's at least one thing in the list, and I'll write if len command parts greater than 0, so we don't get a crash if the user simply pressed enter. If the user pressed enter, the list will be empty, and the program will crash if we try to access the non-existent element at index 0. Now, if the user typed two things, like take book, the second token will be at index 1 in the list, and that's the thing we'll want to shift between inventories. Now, let's pretend I have a function called inventory swap. I'm going to call that if the player chose to take or drop. I'll delete pass from under the two drop and take elifs and write inventory swap Abby sub current location sub inventory, player inventory command parts sub 1, and then inventory swap player inventory Abby sub current location sub inventory command parts sub 1. That's from to item. For take, from current location's inventory to player's inventory, and the item is the second word the player typed. For drop, from player inventory to the current location's inventory, and the item is the second word the player typed. We do have to be careful here that the player typed two words. I'm going to put an if-else here and write if len command parts greater than 1 and indent our function call. And we can write an else with a print statement like you must take something or you must drop something. You can be as helpful as you like. I'm going to leave it at that. Let's write the function. Remember the parameters are from inventory to inventory item. So I'll write this just above the main function. Def inventory swap from inventory dict string string to inventory dict string string item string dash close angle bracket none. That means it returns nothing. And I'll add a docstring under the function header describing what the function does. Now we need to check if the item is in from inventory. So if item in from inventory to inventory sub item equals from inventory sub item. Remember, that's how we add an item to a dictionary. We just say what value will be at that key, and Python adds the key and the value to the dictionary. Then we need to remove it from the from inventory, so we can write del from inventory sub item. I'd also like to print a message, but I don't know if the player was taking or dropping, so I need to pass in another parameter, action, and down where I'm invoking this, I'm going to add taken and dropped as my final arguments when calling this. Now I can add a little message, print item has been action, period. That will say something like book has been taken or knife has been dropped. And then I'll have an else with print I don't see item. That's not as nice as you don't have a item and I don't see an item here, but it's what we're going to do for now. So that method swaps the item between inventories. It doesn't matter what the inventories are. Let's do one other thing, and that's add the inventories to the string returned from getDescription so we know what's in a room. I'll just add to the description, whether it's long or short, if location subinventory, description plus equals, \n, there is a, plus, period \n, there is a, dot join, location subinventory, plus period. That's a little lengthy, I know. I'm using join to join together the sentence, there is a, with each element, but remember join only puts the text between elements, so I'm starting it off with there is a, and I'm ending it with a period. And if I run it and go north, we can see the book in the church. Let's type take and press enter. It says, you must take something. Now I must type this exactly right. If I type take book with book all uppercase, it won't recognize it. But let's take the book by typing it all lowercase. Okay, book has been taken, and it's no longer part of the description. We need to implement the inventory and examine commands. Let's go drop this book somewhere. I'll go south to the cloister and then drop the book. And now the book is in the cloister. Let's implement those last two commands. In my game, I allowed a player to examine an item only if it was in their inventory, but you can allow them to examine an item in the current location's inventory if you like. I'm going to write if lend command parts greater than 1, if command part sub 1 in player inventory, print player inventory sub command part sub 1. Remember, that will be the key, and the value is the description. Examining an item prints its description, and an else on the inner if print you don't have plus command part sub 1 plus period, and an else on the outer if you must examine something, because if we're there, they didn't type a second word. Let's play that and try to examine the book in the cloister, and then in the church, and then after picking it up. And you don't have book, you don't have book, an ancient book with a decorative leather cover. Okay, finally, let's add the inventory functionality. In the game loop, in the elif for the inventory command, I'll construct a string with join for the player's inventory, as I did for print description. So print you have \n\t plus \n\t dot join player inventory, and that will just tab them in a little. Now let's play and go around collecting things. I'll go north and take the book, and then south and take the knife and skull, and I'll type inventory. And I've got all three. So that's a few examples for you of a dictionary data structure. You can see how convenient it is to index into a structure with a meaningful name of an item or other meaningful key rather than an index. And we can do that without losing the iterable qualities that we gained with a list. Now, the order of elements in a dictionary is the order in which they're inserted, so you do lose some power over order. There are workarounds to sort dictionaries, but consider this when choosing a data structure for your application. So, how should you practice? Well, again, I do recommend implementing each location as a dictionary and rewriting the game engine to index in using the dictionary keys rather than indices. I think you'll find that surprisingly easy. And then I would consider playing around with dictionaries a little bit on your own, separate from the game. Create a dictionary of monsters and write a program that allows the player to ask for specific information about a specific monster. Or try writing a little game that allows the player to fight a monster. You could give each monster health points and an amount of damage they can inflict, and the same for the player. Then use the random library to simulate rolling for the player and the monster each round. Drop me a comment if you'd like to see this or some other enhancement to the game once I've finished with the basics. If I can, I'll do a video with enhancements you suggest once I've finished writing the basic engine I showed you in the first video in this series. We still have to look at saving and restoring with JSON and creating an object-oriented version of the game, but then I'll take some fun requests. When you're feeling confident with dictionaries, join me for the next installment of Adventures with Python. As always, have fun and keep coding.